Hello everyone. Welcome back to chemistry class. Let me start with a question. When you look at a chocolate bar, do you ever wonder what percentage of it is sugar, what part is cocoa, and what's just milk powder? In chemistry, we ask the same thing about compounds, how much of each element is packed inside. That's what percentage composition is all about, the percentage by mass of each element present in a compound. Let's explore. We calculate percentage composition using a simple but powerful formula, mass of the element in 1 mole of the compound, divided by the molar mass of the compound, then multiplied by 100. It's like weighing the contribution of each team player in a cricket match scorecard. And remember, this method is the stepping stone to finding empirical and molecular formulas, so it's super important. Think of it as the chemical accountant's job, balancing the books of atoms and their masses. Now, how do we actually apply this? Step 1. Calculate the molar mass of the compound by summing up the atomic masses of all atoms. Step 2. Pick the element you're interested in and figure out its total mass in the formula. Step 3. Divide the element's mass by the molar mass of the whole compound. Step 4. Multiply by 100. Voila, you have the percentage composition. And here's a neat tip. If you add up all the percentages of every element, the result should be about 100%. If it's not, you've probably missed a tiny calculation step. For example, in potassium dichromate, written as K2CR2O7, we calculate its molar mass as open bracket 2 times 39 close bracket for potassium plus open bracket 2 times 52 close bracket for chromium plus open bracket 7 times 16 close bracket for oxygen, giving a total of 294 grams per mole. That's our foundation for the next step. Let's put this into action with potassium dichromate, the bright orange lab chemical we've all seen in jars. Its molar mass is 294 grams per mole. Out of this, potassium contributes 78 grams since there are two potassium atoms, each weighing 39. Now divide 78 by 294, then multiply by 100, that gives us 26.53% potassium. That means if you had 100 grams of potassium dichromate crystals, 26.5 grams would be pure potassium. Isn't that neat? This simple method works for any compound. The only trick is to get the molar mass correct at the start. So whenever you're lost, remember the chain, compound to molar mass to element mass to percentage. Simple chemistry bookkeeping. Now let's try another, calcium phosphate. This one is especially important because it's used in fertilizers and even in some food supplements. The molar mass works out as 3 times 40 for calcium, plus 2 times 31 for phosphorus, plus 8 times 16 for oxygen. That adds up to 310 grams per mole. Out of this, phosphorus contributes 62 grams. Divide 62 by 310, multiply by 100, and you get exactly 20%. So, in every 100 grams of calcium phosphate, there are 20 grams of phosphorus available for plants. That's why chemists and farmers alike care about percentage composition. It directly connects lab calculations to the fertility of soil and the food on your plate. Here comes a big one, nitrogen content in urea, the world's most widely used nitrogen fertilizer. Urea has the formula CO and H2 twice and its molar mass is 60 grams per mole. Out of that, nitrogen alone contributes 28 grams. Divide 28 by 60, multiply by 100 and the result is 46.67% nitrogen. Now imagine you have a 5 kilogram sack of urea fertilizer. How much nitrogen does it really contain? Multiply 46.67% by 5000 grams and you'll get around 2333 grams of nitrogen. That's nearly half the bag. And this, my friends, is why farmers love urea. It's nitrogen rich, cheap, and easy to apply. Isn't it amazing how a classroom calculation explains global agriculture? By now, you're probably thinking, okay, cool calculations, but where do we actually use this? Everywhere. For example, in hydrated salts like washing soda, Na2CO3.10H2O, percentage composition tells us how much of that big crystal is just water. Spoiler, it's more than 60%. In metallurgy, when miners bring back ores, we need to know what percentage of it is pure iron or copper before we even start refining. In agriculture, fertilizers are labeled with NPK values, nitrogen, phosphorus, potassium, all calculated through percentage composition. And in pharmaceuticals, tablets are made with precise amounts of active drug balanced against fillers, again based on the same idea. So, from your laundry powder to your multivitamins, percentage composition quietly runs the world of chemistry. So, let's wrap this up. Percentage composition is simply the mass percent of each element in a compound. The formula is straightforward: element mass divided by molar mass multiplied by 100. Step 1: calculate molar mass. Step 2: find element mass. Step 3: apply the formula. We saw potassium dichromate with 26.53% potassium, calcium phosphate with 20% phosphorus, and urea with 46.67% nitrogen. Beyond the math, its applications stretch across fertilizers, hydrated salts, ores, medicines, and more. So, the next time you look at a fertilizer bag or even a box of medicine, remember, behind those percentages lies this very concept. Mastering percentage composition not only helps in exams but also helps us understand the real chemistry of everyday life. I hope this session gave you a clear, confident view of the topic. Catch you in the next class where we'll dig deeper into empirical and molecular formulas, the next big adventure in stoichiometry.